Hello. Oh God, already. Um, and yeah, and is that the question, the most recent question? Just specify which subject you're talking about, just because annoyingly, again, this month there's a Saturday Sunday split in terms of what we're doing. So everybody, yeah, fine, okay. Um, yeah. So anybody need any questions from the Key Stage 3 stuff? I think they might have been the same actually, the chemistry. They're virtually the same, so it shouldn't be too Um, much different, but I'll just wait for anybody who's got anything else out of these homework things. So, just to be clear, everybody on a Friday and Saturday we were still on chemistry, and then Sunday onwards we've been on physics, which is why it can be a little bit of I've got everything open. That's why got everything ready. But yeah, if you did, yeah. Anyway, if you did chemistry on the weekend, you will be doing physics. If you did physics, you'll be doing math next weekend. Right. I will go through those questions first, which I think is the same anyway, whether you're doing that one or that one virtually. So again, I will once again, as always, if I feel that you should be attempting the question yourself, then I will say so um, and not answer it. Um, okay. So you said 1 to 4. Let's see what's happening here. Right. In chemistry, there is a topic which is to do with how fast a chemical reaction happens. That's what we mean by, um, well, yeah, how fast it happens. And in any practical experiment, you have these things called independent and dependent variables, which you have to figure out by reading the experiment a little bit. So what we're doing in this experiment, we have to read through this method. What we're doing is we're adding some acid and magnesium together. And when magnesium reacts with an acid or any metal reacts with an acid, a gas is given off. Okay. And then what we're doing is we're collecting that gas in this gas syringe. So what's going to happen to this gas syringe is it's gradually going to move out that way as it fills with gas. That's what we're going to do. So let's read what it says. We're going to pour this much acid into a flask. We're going to add some magnesium. We're then going to start a timer and collect the gas in a gas syringe. And we're going to record how much gas we've got every 20 seconds for 2 minutes, right? So for 2 minutes, we're going to keep on writing down how much gas has been collected here and here as this starts to move. And then what we're going to do is we're going to do the whole thing again, repeat that whole thing again with higher concentrations of the acid. So the concentration of an acid basically means how strong the acid is. Um, basically. I mean, that's how strong the acid is. So we're going to use a stronger acid and then another stronger acid and another stronger acid. So we're going to keep doing this with stronger acids and then keep on for each one we do, again, timing it and recording how much gas we're releasing. And so when they ask you for an independent variable, the independent variable in an experiment is whatever we are changing each time we do the experiment. Okay, that's what the independent variable is. What is it that if you're doing an experiment, you must be changing something every time you do it. If you're doing it 20 times, you're probably not going to do the same thing 20 times. You're going to, because that's the point. You're going to be changing something to see whether that change makes a difference. And that's what the independent variable is. So what I always tell people when I do some exam revision later on in life with them, I often say that when you get a question like this, where it tells you what we're going to do in steps, then often the last step will tell you what the independent variable is because it'll tell you what we're going to change next time we do it. So we're going to repeat it all and change this. There's no point you writing the steps every single time. We'll just say, okay, we'll do the same thing again, but we're going to make this little change. And the little change is the concentration of the acid. That is the independent variable here. It's the concentration of the acid that we are using. And then a control variable, in fact, what I'll do is I'll mention the dependent variable first as well, because it's not in this question, but you often will get asked what a dependent variable is. A dependent variable is what you're measuring, okay? So it's whatever you're measuring when you do the experiment. So what are we measuring here? We're measuring the gas collected, right? That's what we're measuring. So that would have been the dependent variable if that had been the question. Now, a control variable is anything that you make sure stays the same every time you do the experiment. So the only thing we're changing each time we do this is the concentration of the acid. So everything else needs to stay the same, otherwise it's not a fair test. For example, this, which is the volume of the acid, should stay the same each time. We shouldn't be using loads more of it. We're just making it stronger. So we're not changing how much of it we've got. We are also keeping the size of this magnesium piece that we're using. There's no point using a massive piece and then a little piece next time you do it because it's not comparing the same things. So you could say the size of the magnesium piece. You could also say how long we do the experiment for. So we're doing it for 2 minutes every time we do it. We're not, doing it for 5 minutes, then for 1 minute, then for 10 minutes. We're doing it for 2 minutes every time. So the time that we're doing the experiment for is also staying the same each time we do it. So that's what that is. Right. And then this shows the results from the first experiment using the acid with a low concentration. So they're showing that at the beginning, obviously, we didn't have any gas. After 20 seconds, we had this much gas. After 40 seconds, this much gas. So that gas syringe was going outwards. And so we were recording every 20 seconds how much we collected. And what you generally find in these experiments, which is why this question exists, is that at the beginning, you get loads more than you do at the end. You see that in those 20 seconds, how much did we get? Extra, none. It stayed the same. In those 20 seconds, how much did we get? One more extra. In those, just seven more extra. Whereas in the first 20 seconds, we made 48 extra. And so at the beginning of an experiment, you tend to get a faster reaction, which means you get a lot more produced, and then it slows down over time. Complete the graph, right? I'm not going to answer this question because you have to draw a graph, which would be easy. How does the rate of this reaction change with time? Well, with time, the rate decreases because what you will find is your graph looks something like that. It'll be something like that. I'm not drawing it for you. I'm not plotting it for you, but you should be something like that. And get slower. And then what we're doing is we're doing the same experiment again, but with a higher concentration of the acid. Now, again, what a concentration does is a higher concentration speeds up a reaction. It makes it go faster. So let's see if that's any of these options is. If you do it with a hydrochloric acid with a higher concentration, then the magnesium will react more quickly. That has to be the answer. Okay. And then we're also saying temperature affects the rate of reaction. So if you do one reaction and then do it the same thing again, but make it hotter, it will happen faster. But here we have to explain it. Okay. So this question probably shouldn't even have been in here. But anyway, we'll carry on because it was not technically either of those topics. But how does temperature affect the rate of a reaction? I'll tell you this. This is a very typical question worth, quite a lot of marks that you always have to, and you have to basically say the same thing every time. You need to say that, firstly, how does increasing the temperature affect the rate? You need to say that the rate increases. It gets faster. But why does it get faster? It gets faster because when you make something hotter, all of those little particles inside have got more energy because they get hotter, okay? So the particles have more energy when you make them hotter. And then, and this gets a bit more technical, if I just try and show you what actually happens that you can't see in a chemical reaction. Imagine these are your acid particles and these are your magnesium particles. What happens in a reaction is that these particles are all flying around, moving. Oh, I can rotate them. Okay. They're all like moving around everywhere, okay, inside your little beaker. And they will sometimes bump into one of the other particles. So in this case, the acid hits the magnesium particle. If they hit them just right, then they will join together and react to make something else. But sometimes, when they hit each other, they won't react together to make anything. So they won't quite react, and then they have to wait until they hit them again. So they have to kind of hit each other at the right angle, effectively. Let me just close this a second because it's slowing down. So these things have to hit the particles just right and hard enough to be able to react, which means that if they're hitting each other more often, more frequently, then you're more likely to get them to react together. So if these particles hit each other a lot, you're going to get a faster reaction. And if they've got more energy, they're going to be hitting each other more often. So you want to say that there would be more frequent collisions between the particles, which will result in the faster reaction. So this phrase, more frequent collision, is so important. Um, yeah, it's so important to be able to say that phrase and understand what it means. It means they're hitting each other a lot more often in the same time. And so you're more likely to get a reaction, and so you get a faster reaction. Okay. And that happens. If you make them hotter, they go around faster and they hit each other more often. Right. 1 to 4, 6, B7. Right. Two. Right. This item appeared in the Wolverhampton Express and Star on October 31st, 1997. Fumes scare at factory. Workers were forced to flee a factory after a chemical alert. The building was evacuated when a toxic gas filled the factory. It happened when nitric acid spilled on the floor and mixed with magnesium metal powder. They want you to name the formula or give the formula of the toxic gas that was produced. Okay, reasonably difficult question, but surely the answer is one of these three things. In fact, no, it's so easy, this question. This is unbelievable, and you shouldn't be asking me this question. I'll tell you why. Um, if it wants the formula of the toxic gas produced, right, in a chemical reaction, the things produced are on this side of the arrow. So they're the things produced, okay? That's what we've made. And if they say a gas, right, these little state symbols tell you the states of the things produced. AQ means it's mixed with water, it's aqueous. L means it's a liquid. And G means it's a gas, which means that is the only answer to the question, right? That's the formula of the gas that was produced. There was only gas produced. You can put NO2 or you can put that 2 in front of it. It doesn't matter. But that's nitrogen dioxide, actually. Explain in terms of particles how the toxic gas was able to fill the factory quickly. This is testing your knowledge really of solids, liquids, and gases. Um, what do gas particles do, right? Compared to solid particles. You know, particles in a solid, they don't move, do they? They stay in a fixed arrangement. You see them, or they move very little. They don't spread out. Whereas in a gas, the particles move, right? So the particles move. So in a gas, I want to say that gas particles can move. So a gas can therefore fill up a space very quickly. You don't want to say spread out. You want to say that because the gas particles can move, I mean, the best answer here really is to think of biology and diffusion. If I've got a bit of a gas in one place, what can it do? It moves and diffuses from a high concentration to a low concentration. It spreads out everywhere, but don't say spreads out. You want to say that the gas diffuses around the factory. I'm not sure how many marks that is. Oh, it's two. Um, Question five was, yeah, I think I want to get to that in a second. I think it might be the same as this booklet. That will be on Saturday, the chemistry app. Fine. Yeah, no problem. Questions 1 to 4. Right, question C. The reaction of nitric acid is more dangerous than if the acid had fallen on the same mass of magnesium bars. Explain why. Right. This is testing your knowledge of the difference between a powder and a big bar of a solid. If I've got a big bar of a solid, right, then I react that compared with if I take that and sort of make it all into like a powder first. Okay, so the same amount, but it's now just in like a powder rather than a big lump. If you do that, then this stuff will react faster than this big lump. Okay, powder reacts faster. The reason it reacts faster is because it has a larger surface area. Okay, that's what makes it more dangerous. Okay, so you have to explain that it has a faster reaction, because it has a faster because it has a larger surface area. Water was sprayed on the magnesium and nitrate to slow down the reaction. What do you think throwing water on something does to it? It cools it down. So you want to explain it lowers the temperature. Okay, and if it lowers the temperature, think of what we said earlier. Earlier we said the particles have got more energy, and so there's more frequent collisions. Now we're just going to say the particles will have less energy if they're cooler. So there would be fewer collisions between them. Collisions is a very important word in this topic. Okay. Um, why is it better to add alkali rather than just water to the spillage? Probably because it neutralizes the acid. Okay, that's what that does. Um, 1 to 4, right. This is 3. Cars cause pollution. So, yeah, 3 different areas. Okay. Which column of data has the greatest range? What is range from maths? It's highest, take away lowest. So what you need to do, I'm not going to do this for you, is you'll need to look at each day, or which column has the greatest range, the column, right? So look at each of these locations, city centre, countryside, motorway, and do highest number, take away lowest number, and figure out which one is the biggest. Explain why the concentration of nitrogen dioxide in the air is lower on Sunday. So if you look on Sunday, these numbers are much lower, right, than the other days. Okay, not much lower, but lower, right? And it tells you the answers in the question if you read the first bit. It says cars cause atmospheric pollution. Some car emissions contain nitrogen dioxide. So if there's less nitrogen dioxide in the air on a Sunday, why might that be? It must be to do with the fact that there's fewer cars or less traffic on a Sunday. And that's why we end up with lower numbers here. And then it says calculate the mean value of the nitrogen dioxide in the air in the city centre for the days from Monday to Friday. So Monday to Friday, city centre means these numbers here. So they've asked you to calculate the mean of those numbers, which means that you should just add them up and divide by 1, 2, 3, 4, 5. Divide by 5. That's it. Um, okay. Right. Nitrogen dioxide is removed from car emissions by catalytic converters. Which two are correct statements? Um, right. Catalysts. Okay. Catalysts. What do you need to know about catalysts? Firstly, they can speed up a chemical reaction. Okay. So they make a reaction faster. So speed up a reaction. How do they do that? They do that by doing something called lowering the activation energy of a reaction. You may remember from the lesson you did that the activation energy is the energy needed for a reaction to take place, and it lowers that energy. So you don't need as much energy, and it will still react. Um, and so, yeah, so that's what it does. It lowers the activation energy, which means that's one of the boxes you tick. The other thing to know about a catalyst is that it doesn't get involved in the chemical reaction. It doesn't get used up in the reaction. You don't see it in the equation. A catalyst is kind of, think of it as just hidden in the background. It's just doing its thing in the background. It's not actually in the sort of things that we write in the reaction. So not used up in the reaction is the other answer. Otherwise, it doesn't do anything else. Um, oh, geez. Unreacted metal obtained from the Earth's crust. Um, the answer is finite resource. I'll tell you that, I think. Um, what is used to test for carbon dioxide? You may know this, but if not, then you will absolutely need to do some work on this soon because it just comes up everywhere. But lime water is the what we use in the test for carbon dioxide. Just so you know, we use a burning splint in the test for hydrogen, and we use a glowing splint in the test for oxygen. So there's 4 gas tests that you will eventually need to know for chemistry. Um, right, and then 1 to 4. Right, let me see if I want to do this. Okay, when you are doing any investigation about temperature, if you're investigating, does it get hotter, does it get colder, then there's a few things you always want to make sure you do. Firstly, you do not want to use a metal or even a glass container, really, because what metal and glass both do is if it gets hot in here, it conducts out of the material of the container very easily, which means it's not going to be picked up by this thermometer. You're using the thermometer to check whether or not it's got hotter or colder, but a lot of the heat will be out here because it's gone through the material. So we want to use something that doesn't conduct heat so well, like you can say plastic or polystyrene, because they tend not to let heat through as easily. Okay. Um, the second thing that you should always do is put a lid on because again, heat can escape out of here as well. So put a lid on any investigation where you're measuring temperature. And then you could probably, let me check what the mark scheme mentions. It mentions everything I just said. Um, yeah, I mean, I would have said that these thermometers are not great. These are the thermometers where a little bit of mercury rises and you have to read off it. Why not use a digital thermometer? Because then it gives you a precise answer um, for the temperature rather than something you're roughly reading off a scale. It just gives you the exact number. So I always recommend that you do that if you're doing these things. Um, I am not going to answer that question because, madness. Um, and then this. I also shouldn't really answer, but I will. There are two types of these graphs. There are graphs that are endothermic or exothermic. The way you tell which one's which is purely by looking at these two lines. Okay. If the second line is lower than the first line, it means that we have lost energy. The energy's gone down. Energy goes down in an exothermic reaction, as in we lose it to the surroundings. Whereas if it's like this, then that's an endothermic reaction because we have gained energy. Energy has been taken in from the surroundings. Um, okay, right, and then there's a graph here. Determine the gradient of the line. I think you should be able to do that by reading the scale, so I'm not going to do that. Why you should not use more than 10 grams of zinc. I think according to this graph, if it continues like that, if we use 10 grams of zinc, I mean, it's getting pretty hot. At 80 degrees it's getting to. So you probably shouldn't do that because it might get dangerously hot. Um, yeah, something like that. It's going to be too hot, too dangerous, that sort of thing. Um, right, that was for that. Right, let me just do something else. Somebody, if you have questions anyway on the homework, that's the purpose of this, by the way. Um, to tell me if I don't go through something. Um, 6B. Actually, I'll tell you the answers here. So again, a difficult question. This is about this thing called cracking. Cracking is when I've got like a long hydrocarbon like C10H22. These things that are long are generally not that useful to us. We tend to want to make them smaller. So I can make that smaller and turn it into something like C8, which is not much smaller, C8H18, and something else, which is like C2H4, that they do in this question. They turn the longer thing into these two smaller things. These tend to be more useful to me. That's why I like to do that. So we do something called cracking. Now, cracking, I mean, there's really only two things to try and remember about the process of cracking. You want to remember that we need high temperatures and a catalyst. With those two things, you can turn a longer hydrocarbon into a shorter one, which means that's basically what this is getting at. In this question, this pottery acts as a catalyst. The name of the liquid hydrocarbon produced by the cracking, the name of the liquid hydrocarbon produced by the cracking. Isn't there two of them? Let's check what it wants. Um, it wants octane. This one here. Oh, okay, that's not great. But the name of the alkene produced is ethene. It's that one there. An alkene, remember, has this general formula where you double the C's to get to the H's. Right, I think that covers everything you wanted. Well, seven. Um, I'm not answering the first question. I'm not going to answer that question. Um, yeah, not going to answer that. Complete combustion is a process that looks like this. Let me just tell you this. This is important. Firstly, the word combustion just means burning. That's all it means. Okay, well, there's two ways in which something can burn. Oh, more questions here. I'm not going to do bio paper one AQA. The purpose of these lessons, just to be very clear, is mostly to go over topics that we have done in the lessons that you have had recently. Um, that's the majority of it. Where I have time, we can try to do some other stuff, but I need to make sure it's relevant and we have to stick a little bit to the syllabus that we follow. We have been doing, just to be clear, bio paper one topics every single week for a year. So, I mean, not every single week, every single month for a year. Oh. Okay. Complete combustion is burning, but it's burning. Any sort of burning requires two things. It requires fuel and oxygen. These alkanes, these things are all types of fuel. Okay. Um, so when you burn something, it can only burn if you have oxygen in the air, and obviously we have plenty. So it needs oxygen for burning to happen. Now, if we have lots of oxygen, then we get something called complete combustion, where we get carbon dioxide and water only as the products. It's relatively clean, it's good. I know carbon dioxide is a problem, but relatively speaking, it is the better way of burning stuff if we have lots of oxygen. But if we have not very much oxygen, so less oxygen, then we get something called incomplete combustion. So fuel plus less, I want to put oxygen is. Now, we still get carbon dioxide and water when we burn something with a bit less oxygen, but we get two more things, sadly. We get some carbon and some carbon monoxide. These two things are worse for the environment. Carbon monoxide is a poisonous gas. Carbon causes these particulates to go into the air. It's called global dimming when that happens. And that's what happens when we do incomplete combustion. Um, Bullet points generally no. You don't lose marks writing in bullet points. As long as all I say about bullet points is just make sure that your bullet points make sense. Because it's very easy to, when you're doing bullet point stuff, it's like you know what you mean, but the person reading it might not know what you mean because you abbreviate it a little bit too much. So just make sure that bullet points in principle are fine, but it's just say a sentence still. Like just, make sure it makes sense in terms of what you're saying, that the person reading it can make sense of it. So incomplete combustion produces a couple of extra products which are slightly worse for the environment. The example of this, which I just want to mention to everybody, is a Bunsen burner. A Bunsen burner basically has two settings. You can open the air hole or you can close the air hole. When you open the air hole, you're letting in more air and therefore more oxygen, which means you get complete combustion because there's lots of oxygen coming in, and therefore you get that clean blue flame, which is what we always use because it's just better. If you close the air hole, you are letting in less oxygen. And that's when you get a different flame. And you get the different flame because you're not burning it as well. And therefore, you're getting some incomplete combustion in that situation. And that's why you get the yellow flame that we don't use because it's just not as good. It doesn't give us as much heat. It's not as hot, literally. Um, and yeah, and also if you use that yellow flame on a Bunsen, on a beaker, then you're going to get like blackness. It'll go all black, and that's the carbon that's being produced from that burning. And you don't get that as much, at least, from the other flame. So that's what that is, right? It's a long-winded explanation for a simple question, which says complete the word equation for the complete combustion of methane. When it says complete combustion, you know now there's only two products. They are carbon dioxide and water. And then it says what different gas is produced by incomplete combustion. And that's when you want to say carbon monoxide is produced when you, um, that's the other gas that's produced from incomplete combustion. Right, that's basically everything, isn't it? No, I'm not going to do ballot paper one AQA. As I say, I'm not going to be doing that today. There are lots and lots of resources that you technically have access to, but if you want to message us about it, then you can get quite a lot of videos and stuff. I just don't know if everybody has them still. I will sort it out for this summer, um, in which you can watch quite a lot of content in relation to all of those things, should you need to. Um, But if you don't have access to these things, then just contact us. If you don't, if you have no idea what I'm talking about, you on our website you can log in and watch loads of videos on all of this stuff. It's literally like, you know, cells or respiration or circulation or digestion or disease. I've made videos on all of these things. So if you like the way I do it, then that would be the thing to watch. Um, if not, just go to YouTube and type in biology paper 1 AQA and you'll get a whole tons of millions of resources on it. Right. So let me just check if I've answered anybody else's question. Yeah, 9, 5, and 6. I'm just making sure if there's any different. Otherwise, that's it. Um, okay. Oh, it's different slightly. Yeah. So let me talk about this question. Complete the word equation for the combustion of hydrogen. I mean, the best answer here is water. Hydrogen and oxygen make water. Don't they? So, right. And then one of these graphs, same graph again. Um, now, if you had to say, is this exothermic or endothermic, you should hopefully say exothermic because this line is lower than that line. But there are some other key labels that you need to make sure you recognize, which is um, the distance between here and here is what we call the overall energy change, okay? Which it doesn't ask you for, but it asks you the overall energy change. So it tells you whether we've gone down or up and by how much. The activation energy, every chemical reaction has to increase in energy before it starts to react. That's the activation energy. So all both of these graphs, whether it's endothermic or exothermic, sort of go up and then come down a bit. Now, how much they go up is called the activation energy. So in this case, that's the activation energy, which is A. What type of reaction is shown? Exo, as I said, and what you want to say for that in words is because the energy of the products is less than the energy of the reactants. Okay, so energy of products is less than energy of reactants. There is a very abbreviated answer. And then for this reaction, the value of A is 1370 and C is 3230. What is B? So A is 1370. C is 3230. And they've asked you for B. Well, I mean, it's like a number line almost. This one is 1370. This is 3230. So surely B is the difference between those two. So 3230 minus 1370 is 1860 should be the answer. Okay, ruin that. Um, again, this looks like a complicated question, but it just isn't. You have to read the graph, say what number it is up to. That looks like 22.5 to me. The final temperature looks like 38.7 to me. The increase in temperature, the difference between those two numbers, which is 16.2. Okay, then you go to this, and even if you don't understand any of this, which you probably won't at this stage, you should get the question right, as long as your maths is capable. Because it says the student worked out the heat energy released by burning. Oh, actually, no, that is quite complicated, actually. The heat energy released by burning 1 gram of each alcohol. What is the value of M? Well, it's. Let me just check if that's what they want you to say here. Um, 5CIR. Um, did I tell you in this question something? There might be the answers earlier on, I think. Yeah, there. Horrible. But yeah, it's the answers there. So the M is the mass of the water that we're using here. So that was meant to be 50. Okay, from the, yeah, just do it on the picture. Which value is anomalous here? I'm not reading all of this. This is a little bit complicated, but anomalous means something that doesn't fit. Now, as you can see, we increased there. It went up, then it went up, then it seems to have gone down suddenly, right? Which seems unlikely to happen. So I would say that oh no, sorry. we're talking about. That's not right. It's gone, it's going up by a couple and it's going up by a little bit. This seems to have gone up by way too much, right? It's just out of place, isn't it? Because we're going up 11 to 13 and then 20 and then it's going down again. It's like that seems out of place. It doesn't seem to fit the pattern. It's way too high. So that's the value that we want to put there. Okay. And then what is the relationship between the number of carbon atoms and the heat energy released? As that's going up, that's going up. So you just say, as the number of carbon atoms increase, the heat energy increases. You don't need to understand this to get the answer right. Um, and then sometimes when you do an experiment, it doesn't match what a textbook might tell you the answer should be. And then you have to look back at this and look, remember what we said earlier about any experiment involving temperature. There are certain things you should do, like um, use a lid, not use a glass beaker. I know it doesn't say glass beaker, but you could insulate it a little bit. So insulate the beaker a bit because you seem to have lost heat and your values won't be accurate. So that's the kind of things you want to say for that one. Um, and then there's only one more, I think. 6. Okay. I think I did the second part of 6 already. First part I've not done. So I'll just fill these in. Some of the products of cracking can be used in cars as fuels. The products include alkenes and saturated hydrocarbons called alkanes. Alkenes can be used in reactions to make large molecules called polymers. Again, you wouldn't have done a lot of this. It's fine. The many small molecules that join up to form a large molecule is known as monomers. That's what you want to say without the arrows. Um, doing all of that. And then I already did that one. So I think that is all of question 6. Um, fine. Right. There doesn't seem to be any more specific um, questions. Um, yeah, I know a couple of you asked about other topics and things, but what I would, it's just, I would advise that um, we will most likely, at any time, you don't have to do it on a Wednesday, but any time if you say that you need some notes on this, then it's very easy for us to put together a quick, like I think one of you mentioned the ceramics thing that I did the other day to go over. Um, and but I can send some textbook notes on it. It's just that I won't always be able to do it in these lessons. I need to focus on the homework things, and that some of that stuff is way beyond what you'd normally do at this point. And same with like you mentioned the biology paper one AQA. If you just send us an email or something saying that you have any videos or resources for that, then we can just make sure that you have access to it. I can double check that. It's just I need to do it for everybody individually. So if you do that, then I can always do that. What grade should we be getting in year 10 mocks? Well, that's an impossible question. I would say that it's year 10 mocks. Um, I would hope that, I mean, for you in particular, I would hope sevens and above. I would hope. Yeah, it's all on the person a little bit, isn't it? But yeah, I would say probably something in that sort of ballpark. You don't want to be significantly below that, partly because if you are significantly below that, like if you're on a fives and stuff, then a conversation starts to happen about higher and foundation level, which is not really a conversation you want to have. Um, so you kind of want to comfortably stay above that. That's where I would probably say would be the answer. Right, that is all I'm able to do today. As I said, just anytime, not just on Wednesdays, but just if you need resources on something, then just message. We can put together a few notes and stuff for you to read through so that you have that. And if you don't have access to the videos and stuff that you will have definitely over the summer, because I will check everybody individually. But if you want them desperately before that, then send us something. I know it doesn't cover every single topic, but certainly at this stage, it covers most things that you will need, and I will be updating it over the summer anyway. Right, that's it, I think. Given that nobody else has any other questions.